In this video, I'll take what I've taught in the last two videos and put it all together in order to solve this practice problem. It says a six-stage distillation column is designed to separate a 100 mole per second saturated liquid feed that is 30% A, 70% B. The relative volatility of the components is 2. The distillate product is 80% A, the bottoms is 8% A. The reflux ratio from the total condenser is 10, and the feed enters on stage 4. Find all flow rates and compositions of interstage flows. So I'm going to draw my process flow diagram in the way that I told you to draw it, which is one big rectangle. And I have 6 stages in this column, so I'm going to need 6 stages. 1, 2, 3, 4, 5, 6. Numbered from the top once again. And that's important too, by the way, because stage 4 has to be the 4th from the top, not the 4th from the bottom. So I have my feed coming into stage 4 at 100 moles per second at a composition of 30% A, 70% B. We can leave that off the process flow diagram because that part is understood. I have a total condenser at the top. And it says total condenser, so I don't have to figure out whether it's partial or total. And it is refluxing at a reflux ratio of 10. R is equal to 10. I have a distillate product of unknown flow rate, but I know that XD is equal to 0.80. And at the bottom of the column, I have to draw my reboiler. And my bottoms product is an unknown flow rate, but my XB is 0.08. So at this point, try to pause the video now and see how far you can get with this. So in other words, see if you can solve any of the unknown variables, keeping in mind that this is asking me to find all flow rates and compositions of the interstage flow. So I'm going to have to find V1, L0, so on and so forth, V6, Y6. Actually, this is V7, Y7, right? Because it's coming from the reboiler. L6, X6, and all stages in between. So like I said, go ahead and pause and see if you can work out as much of this as you possibly can. Now, if you haven't paused yet, I'll give you a slight hint that the overall system is going to be where I choose to start. So by drawing my box around the entire system, that is going to allow me to solve for a couple of variables right off the bat. So performing a degree of freedom analysis around the entire distillation column tells me that D and B are my only 2 unknowns, and I have 2 material balances that I can write. So once again, here, seriously, pause the video now and get your practice in. Students are always asking me for more practice. Practice finding D and B by performing overall material balances. Are you still watching? Why are you still watching? Pause the video. Solve for D and B, overall material balances. Pause the video. Do it. Let's go. Okay, I'm just messing around trying to have some fun with the online semester. I'm going to show you how to do it, right? So D and B are my unknowns in my overall system. I've got 2 material balances to solve for them. So I'm going to say 100 is equal to D plus B, and my component A material balance says 30, so that's 0.3 times 100 is equal to 0.8 times D plus 0.08 times B. System of 2 equations, 2 unknowns, solve. Okay, the result there is D is equal to 30.6, B is equal to 69.4. So those can both be entered into my process flow diagram. 30.6 and B is equal to 69.4. Next thing to do is to figure out what I can solve for next. So if I have any relationship that I can use, I'm going to go ahead and use that. And in this case, what I've got is L0, and I'm sorry, I have my R. Remember I said in the previous video that R is equal to L0 over D. And now because I know that R is equal to 10 and D is equal to 30.6, then I must know that if I solve for L0, I've got 306 moles per second for L1. Now that I have L1, I also have all the other L's too. So I've got L1 is equal to 306. L2 is equal to 306, so on and so forth. Right, so all my liquid flow rates all the way up until I hit L4. Now what's going to happen at L4 is, does it tell me what the feed is? It does not tell me what the state of the feed is. Actually, I'm going to leave that till next time. So depending on what the state of the feed is, that is going to affect what our balance is that we write for L4. Let's keep going. Now that I have L naught and I have D, I can write a condenser balance. So instead of my overall material balance, shouldn't have drawn that as a dotted line because that's going to be a pain to erase. I can now do a balance on the condenser. Condenser balance says that V1 is equal to 306 plus 30.6. In other words, is equal to 336.6 moles per second. It's probably a few more significant figures than I usually like to keep, but that's okay. And now since I know V1, I now know all the vapor flow rates as well. 336.6, V2 is 336.6, so on and so forth. Once again, I'm going to stop short from going to the stripping section because I haven't actually told you what the quality of the feed is what it's called, whether the feed is a saturated liquid or a saturated vapor. Again, we'll get there. All right, what other relationship can I describe now? Because this is a total condenser, first of all, I have a split point here, right? So in a split point for material energy balances, we should be able to relate what X naught and XD are. And because it's a split, the split point is right there, I can say that X naught is equal to XD. So let's say X0 is equal to XD is equal to 0.80 because there is a split point. And the split point does not affect the compositions of my streams. I just taught that in my MEB class, by the way, so that's fresh in my head. Because of the split point not affecting composition. Okay, so now that I know what X naught is, now I should be able to say what Y1 is. So I could do a material balance here, or what I could do is realize that because the condenser is a total condenser, well, this little stream right here I have to keep track of. First of all, V1 is equal to the flow rate of this little stream that I just circled, going from the condenser to the split point. But the composition Y1 is also going to be equal to X naught and XD. So Y1 is equal to X naught is equal to XD is equal to 0.80 because a total condenser does not affect composition either. Okay, all that's happening here is the condenser is taking it from a vapor to a liquid. So we're going all the way through the equilibrium region and the composition is unchanged. Okay, now that we have our stream coming into the column from the top and our stream coming out of the column from the top, now we can start to work through our balances. All right, so key, we know what Y1 is. And as I said before, streams that come off of the same stage are in equilibrium. So therefore, I can write a relationship that says that Y1, which we now know is 0.80, must be equal to alpha x, and alpha is 2, as the problem said, 2 times x1 over 1 plus x1. Or that's the simplified version. There's a 2 minus 1 there out front, but that is equal to 1. So I can now solve this for x1. And I think I'm going to leave the calculation part to you. Well, actually, you know, it's going to be informative if I tell you what it is. So x1 is equal to 0.667 is what I got. And now because I know the flow rates of everything coming into stage 1 and everything leaving stage 1, and I also know the compositions of the liquid coming into stage 1 and both streams coming off of stage 1, I can write the following material balance for Y2 coming into X2. So by material balance on stage 1, I can write the following. Y1 V1 plus Sorry about that. My dogs are distracting me. Y1, let's see, we know everything here except for Y2, right? So I should be able to plug in everything. Y1 was 0.80. V1 was 336.6. X1, we just solved for, was 0.667. L1 was 306 equals Y2. V2 is 336.6 plus X naught is 0.80 and L naught is also 306. So you should be able to solve this one now for Y2. Solve for Y2. And this is equal to 0.679. All right, so I still know all the flow rates, and I'm working my way down the column. I'm going to start boxing some answers. My next order of business now is because I know everything coming off of stage 1. I now know this stream as well. And because I know this stream, I just solved for Y2. I can now say Y2 is in equilibrium with X2. So equilibrium relationship, Y2 is equal to 2 times X2 over 1 plus X2. And that is all equal to whatever I just said it was, 0.679. All right, solve this equation for X2. And you get 0.514. All right, now I have a material balance I can write. MB on stage 2. And you quickly see how once you've got the pattern established, it's really not that difficult. However, it is very tedious. So I've got an equilibrium relationship, material balance, equilibrium relationship, material balance, all the way down the column. So I'll just do this one for you, and then I'll allow you to use your imagination to solve the rest. Y2 V2 plus X2 L2 is equal to Y3 V3 plus X1 L1. All right, and I can use this to solve for Y3, which is 0.50. So hopefully what I'm demonstrating to you now is that solving a distillation column is nothing more than an alternation of solving a material balance, solving an equilibrium relationship. And while it's possible to do so manually, algebraically, it's not very fun. I'm getting very bored, and it's very tedious for me to sit here and write out all these balances. So this is what I was talking about in the first couple of weeks when I said if you can think of an algorithmic way to do it, it's going to be a lot easier and smoother. And I've also realized that because I haven't told you what the state of the feed is, I actually can't go through and solve for the bottom without making some assumptions. So I'm going to stop this video here, and I'll give you the message of hope that next time when we come back, I'll talk about the graphical way that you can start to solve these distillation column problems. It's going to be a lot smoother and easier, but you should never lose sight of the fact that when you're solving graphical distillation problems, you're doing nothing more than alternating solving a material balance and an equilibrium relationship. That'll be all for this video and all for this class. I'll see you in the next class.